Well, that's what I'm saying. Maybe I'll turn off the video in the last 10 minutes and tell you guys what's going to be on the exam. All right, so today what we're going to focus on is we're just going to sort of finish up aromatic chemistry, and there's really not too much that's going to be new today, but one of the things that we're going to sort of focus on is how substitution, again, we talked about orthometapara in terms of substituents around the benzene group. What we're going to talk about now is a couple more reactions, but then we're going to focus on how substitutions and certain types of substitutions can actually influence regiochemistry in terms of how you might get selectivity towards a specific set of compounds. But again, at the end of last class, one of the things that we kind of focused on as a theme, right, is that sort of electrophilic aromatic substitution often focuses on treating these molecules with really strong electrophiles. And oftentimes these electrophiles, there seems to be this trend that we see where these are like almost cationic in character, right? So things like bromine that would otherwise not react with it, you take it and you treat it with aluminum trichloride, or some Lewis acid that effectively takes it and makes it into a sort of, gives it that high cationic character, right? And then again, the mechanism is simply going to be, again, there's usually some counter ion that goes along with this, but the intermediate's effectively going to be that you are going to again have that double bond. Again, this is analogous to alkene chemistry, so you can sort of think about it at least in terms of drawing, similar to the alkene chemistry. And then the two possibilities, right, are if you have some nucleophile that can add in, that would be what often happens in terms of the alkenes. But one of the things about aromatic substitution is that aromatic groups are very stable, and so instead what ends up happening is a E1 type elimination process that effectively completes that mechanism. And so again, what's going to abstract that proton? You could think about it as being a bromide. If it's something like our chloride, it's effectively going to be, at least from a mechanism standpoint, whatever in a way, whatever the sort of Lewis acid sequestered. So again, we saw this in a few cases, right? We saw, for example, bromine by itself will not react, but if you take it and you treat it with iron trichloride, this will effectively coordinate to the bromine, making that bromine an even better electrophile. Bromine's already a pretty good electrophile, but the iron trichloride makes an even better electrophile, right? And then what's going to happen is you're going to brominate that. Again, and then we also saw a parallel with halogens, right? So sort of Friedel-Crafts chemistry, so whether it's an acyl chloride or whether it's an alkyl halide, you'll take these compounds and treat it with aluminum trichloride. Again, I think for the sake of what's going on here, I wouldn't necessarily try to memorize iron trichloride or aluminum trichloride. Just remember that it's sort of one of these. If on an exam you accidentally write aluminum trichloride with bromine or iron trichloride, here I'm not going to penalize you guys because it probably would work, right? So I don't know why they didn't just stick with the same, but there might be some subtleties in terms of the chemistry. But for your guys' sake, it's just important that you have this Lewis acid, right? And then you're going to sort of alkylate that. And then we showed that there's other means in which case we can get access to cations that we're aware of. And one of those was take these molecules and treat them with, right? We take these molecules and we treat them with, say, for example, an alkene and some source of acid, like perhaps sulfuric acid or triplet acid or something like that. what's going to happen is we'll get to sort of a branched alkane like that. And again, this is going to take place via this sort of carbocation, right? It's generated through protonation of the alkene, reacting with it. Right, and then again, probably our conjugate base from here is going to go and pluck that off when we get here. Okay, so there's a sort of theme of activating things that would otherwise not be great electrophiles, getting them to react. The other two that we'll sort of show you guys has to do with making carbon heteroatoms, and specifically carbon nitrogen and carbon sulfur. And so as it turns out, if you take benzene, one of the things that you can do is treat it with nitric acid. Right, so if you take this and you treat it with nitric acid, again, I'll draw it out and show you guys exactly what's happening. Sulfur trioxide. By themselves, these would not react with these, but in both cases, if you treat it with sulfuric acid, you will actually begin to start getting some chemistry. Okay? And what's going to happen is that you're going to start to get chemistry that involves nitro groups. Again, I'll show the mechanism of this in a second, but I just sort of want to put this in perspective for you. And in the case of this one down here, what you're going to get to is sulfonic acid. Okay. All right. So how does this work, and why are the acids important? Well, let's draw out nitric acid, and we can effectively see what's going on. All right. So nitric acid is one of these interesting molecules in terms of the fact that it's got that sort of positive charge on nitrogen and negative charge on oxygen. So that's perhaps one of those compounds that's a little bit counterintuitive to sort of draw out, but that sort of structure. And what happens is when you take this and you treat it with sulfuric acid, I'll just put H+, what's going to happen is you're actually going to protonate that acid, so sulfuric acid's pretty strong. What will happen is you will again, this would probably protonate at first, I get that, but it's going to be a reversible process, and over time what's going to happen is you'll get here and you'll generate again, this molecule here, okay? And so this is a sort of a souped up electrophile. So basically what you've taken is nitric acid and you've turned it into this molecule that has very high cation character. And then what's going to be able to happen is, I'm not going to go through the whole mechanism, but it's just going to be analogous to what we've seen in the past. Okay, so we're going to be able to attack that now, and we will get to ultimately the sort of nitro group here. Okay? In the case of sulfur trioxide, the sulfuric acid is also going to help increase the electrophilicity of this. So what will happen is here's sulfur trioxide, okay? So again, it's sort of neutral in the same way that nitric acid is neutral. So what's going to happen in this case is that you're going to treat it with sulfuric acid, okay? And what that's going to do is it's just going to activate, right, the compound, again, giving it this high positive charge character to it, right? Now that we have this sort of more charged, better electrophilic species, what can happen is the benzene is going to be able to attack, right? And then, again, on and on through the mechanism, you'll end up with, of course, here, sort of sulfonic acid, which will then again aromatize. So all these mechanisms should feel very analogous to one another. And again, that's one of the keys to organic chemistry and all these different reactions is thinking about the mechanisms, recognizing these mechanisms, and specifically how the mechanism can relate many of the different reactions and sort of show how these shouldn't all be their own sort of exclusive reaction. So again, we saw previously with carbon, making carbon-carbon bonds, and so here we have a couple examples with nitrogen and with sulfur. Okay, any questions? Okay, yeah.
That NO2 over there, that's super electrophilic.
Yes. So it's a better electrophile.
Could the positive is on nitrogen?
Well, it's always, the positive's always on nitrogen. But the thing is that with this new compound, the overall species is positive. So the overall molecule wants, right? Like there's a positive charge on the nitrogen here, but it's sort of counterbalanced by this sort of negative charge in the oxygen. So the overall molecule has this neutral charge, whereas in this species, the overall molecule is sort of positively charged. Yeah. No, that's what I'm saying, is that you need to sort of generate this more active species. A lot of times they'll actually even draw even more charged. They'll call it like HONO, so you'll actually even draw like this positively charged as well, which might even illustrate it being even more charged. In fact, that might even be what the book does, HONO, H-O-N-O. But the overall idea here is the same, is that you're sort of using that acid to sort of activate the sort of complex. And again, you could imagine the HONO, right? Like I said earlier, right? This would probably be protonated first, right? So in truth, maybe that is what needs to happen. I guess I was just trying to simplify it, but this would be protonated throughout the process first, followed by this one. So probably what you would generate is something like this, right? And now hopefully you can definitely see how electrophilic that is, right? And then this is, I think, this is actually probably what it more really is. And you'll see this, it's got a catchy name to it, HONO, which is just H-O-N-O. So maybe that'll help you remember it. Okay? Any more questions? Okay, so because of the fact that this is cation, effectively cation-like driven transformations, what's going to happen is there's going to be certain electronic features to these molecules. So if you could imagine a situation where you say, for example, reacted HONO, and just for sort of, let's just say, H-O3N and H2SO4. Again, this is a molecule that is neutral, well, as far as benzene goes, it doesn't really have anything on it, it's just benzene, right? You're going to generate nitrobenzene, but because of the fact that you have a good electrophile, as you might imagine, depending upon substitution around this benzene, that's going to have a direct impact on how fast or how poor the chemistry is going to take place, right? And so if you have a more electronically rich alkene, for example, it will react faster with different electrophiles. And it's the same thing with benzene, right? If you have a more electronically rich aromatic ring, it's going to react a little bit faster. So as you start to put groups onto here. Say, for example, toluene, right? Toluene now effectively allows sort of stabilization throughout this system, makes it a little bit more charged. The overall process, and I'll just say NO2, and we'll get into the regiochemistry in a moment. I'm just saying that somewhere on there, we'll specify the regiochemistry. This is going to be a much faster reaction. And we'll discuss, this just means anywhere on the ring. We'll discuss, there is regiochemistry that we'll discuss in a moment. I just want to talk about the sort of kinetics right now. Meanwhile, if you do the same chemistry and have something that would be electron withdrawing, it's going to have the opposite effect, right? And so if you have, say, for example, a cyano group, right, or say a ketone. Did you hear someone singing? Coming through the vent? Was it you? Oh, it was your phone. I thought it was coming through the vent. I thought it was something next door. Okay, so anyway, sorry to embarrass you. But if you have an electron withdrawing group, again, it's going to be the exact opposite, right? You're sort of pulling electron density out of the aromatic system. Thus, it doesn't have as much electron density to donate to make new bonds, right? So this is going to be a slower reaction. And so oftentimes some reactions so slow that oftentimes certain reactions like Friedel-Crafts, for example, becomes even more sluggish and you actually can't even get it to go. So the book discusses this a little bit. Friedel-Crafts chemistry will oftentimes not even work. You won't even be able to get it to go when you begin to have electronically poured. So electrophilic aromatic substitution certainly works best with sort of donating groups, okay? And so that's oftentimes where you're going to see it done. The other thing about having donating groups to the aromatic group, to the benzene, again, if you're starting to make more substituted compounds, is that there's going to be a certain regioselectivity as well. So electrophilic aromatic substitution. Okay, and so previously, one of the things that we did when we were talking about Diels-Alder reactions, right, is that we began to discuss delta positive, delta minus, sort of where there is charges based around alkenes, right? And so we talked about, say, for example, an ester, right? If you remember, we were talking about the regiochemistry of Diels-Alder reactions. And one of the things that we said that we could do, right, is really think about the two resonance forms that you could generate, right? So you can push the electrons onto one alkene, or you can push the electrons onto the other alkene, and sort of look at the relative stabilization of these two compounds. So in the blue case, again, we're pushing the electrons onto that. We're pushing the electrons onto this primary carbon. In this other case, we're pushing electrons onto the secondary carbon. And we sort of looked at these and we asked ourselves, right, we looked at these two resonance forms and we started to ask ourselves, well, which of these two resonance forms is probably more happy? Which is a better representation of the electronics of the system? And in fact, whichever one looks better may be a better indication of the dipole of the system. Right? So when we looked at these two, we asked a couple questions. Well, we recognize that carbonyls have a nice delta positive here. So even though that this is secondary, that positive charge here is actually going to destabilize that group here. And then meanwhile, in terms of the negative charge, that actually ends up being pretty good, right? Because in fact, we can do resonance donation. Some people brought up cation being perhaps more stable in a secondary carbon, and I think that's good to think about that. But again, there's this competing factor that's the carbonyl dipole sort of creating a positive charge there, further destabilizing that. So in this case, what we see, right, is you can sort of draw it as a delta minus on that carbon and a delta positive on that carbon. Again, that's going to sort of explain some of the regiochemistry that we get. And again, if we do the same thing with an electron donating group, like say, for example, we put a methoxy group on there, one of the things that we can do, right, one of the things that we can do is the same thing. Right, we can put that negative charge on the methoxy group, or we can put the negative charge on the other side, right? And as we look at these two, it should become fairly apparent, right, that this is going to be the more stable of the two, in part because we have that nice resonance stabilization for that, and thus this structure is the one that's going to be more representative of the sort of overall dipole of the system, right? And so what we would have here is a delta minus here, and a delta positive here. And again, some of you may have other ways to look at it. I saw people just going directly and sort of saying, okay, look, you can push these onto that carbon. It's basically saying the same thing, right? It's just looking at it in a little bit different way. It's sort of showing how this electronics can effectively stabilize ultimately that carbocation, right? It's sort of stabilizing this resonance form, saying the same thing, just a little bit different. Okay, so I often think that resonance forms and looking at the resonance forms and looking at the relative stabilities is certainly something that you guys should be able to do. It should be something that you are fairly comfortable to do now. And we can do the same thing to start explaining regiochemistry of electrophilic aromatic substitution. Okay, and so if we have a molecule that has, say, for example, a methoxy group on it, in this case, it becomes a little bit more complicated, right? Because what we have is 5 carbons rather than just the 2. But the same principles will apply to sort of being able to assign partial negative and partial positive charge to the system, right? And so, say for starters, let's just try to keep it analogous, and I'll just sort of come from the middle outwards. Right? If we go the sort of blue direction there, or the green direction here, right, we will get a couple different compounds, right? In the case of the blue, we'll put our negative charge there, and we'll put our positive charge here, right? And in the case of the green, we'll put the negative charge right, in this case, what we're going to do is we're going to put our negative charge here and a positive charge here. Okay? And when we look at these two compounds, we notice a huge analogy to what I drew previously, right? And you should all be able to sort of see that of the possibilities here, right, just focusing on this alkene, right, that this would more likely be representative of what the electronics would be, right? And so if we begin to try to assign dipoles around this system, right, we can start to think about a delta positive there, and we can start to think about a delta negative here. But it turns out that this sort of charge, right, as you start to look at the charge and the charge delocalization around the system, we can begin to see how there becomes a pattern within this benzene group, how 3 carbons have a negative charge, a delta negative, and 3 carbons have a delta positive, right? And so if we, say, for example, draw this resonance, right, we will get to we can see that you can also put a negative charge. Just drawing that resonance form. You can see that you can also have a negative charge on the sort of paracarbon, right? So we should start using those terms to get comfortable with them. So you can see that the position ortho, right? This position here, ortho to the methoxy, has a negative charge to it. But you can also see through the resonance that the para position also has that delta negative charge to it. Okay? And furthermore, you can then, again, because of the symmetry, you can sort of see that you can also put that negative charge present to the other ortho. And so what happens here is you effectively have a delta negative charge at every other sort of carbon on the system. And in general, as you're sort of going through pi systems, there's often this changeover, delta minus, delta positive, delta minus, delta positive. There are examples where we have electronically confused, as we like to call it, species, but in general, this is something that's fairly standard. So the carbons that we've illustrated here, here, and here, right, are the three carbons that have the best and most electron sort of rich nature to them. And so when the chemistry takes place, it's generally these carbons which are going to act and behave as a nucleophile. It's really the bonds are really going to be forming into these three positions. Okay. Now we can go through a mechanism with this. First of all, any questions? Yeah.
I just want to say that it's your plan and outcome is going with it, and you're producing a calculated method.
Yeah, so because this isn't, right, so in this case, right. So this would be effectively the resonance form that would right, so that would effectively be the resonance form that would show, thank you, that would show the meta, right? And then again, you could push this over to the other meta as well. But you can clearly see that that's actually the less stable of the resonance form. So if you go through the same thing through the other one and start putting the negative charges at the meta positions, that's where the negative charges end up here. And again, we know that this isn't as good as the others because in this sort of resonance form, we don't really have this same type of stabilization. And you're going to notice the same thing would happen if we had a methyl group there, right? Why? Because if we had a methyl group there, well, it turns out that you can put that carbocation on the more substituted position, right? So a methyl group is also considered donating, even though it's not resonance donating. By having that methyl group there, you're going to sort of also have this directing group via putting that positive charge at this position. So again, I think that looking at the resonance forms, thinking about where the negative charge is and where the positive charge is, and then using that to effectively understand how the dipole is around the system, where that delta negative is, where that delta positive is, can really help you explain the chemistry, right? And so, and we'll go through this mechanism in a little bit more depth in a moment that would help further sort of illustrate this. But again, if you're going to do this reaction, you're going to run this reaction, you're going to get a mixture of products. Say, for example, you did, again, HNO3, or actually just to stay broad, we'll just use this sort of standard electrophile plus to sort of say any of these different things we saw, whether it's Friedel-Crafts or generating nitro or sulfonic acid. We're going to get a mixture of compounds that will be, in this case, a mixture of the meta. So again, if we did it on the other side, it would be the same molecule, so I'm not going to bother showing that one. But effectively, we get it at all three positions, okay? And the ratio that we might get, and that's going to vary depending upon the substrate. You might assume there's a couple competing factors here, right? And so it's kind of difficult to really predict, but stoichiometrically, right, you might expect two equivalents of this to one equivalent of this just because there's two positions, right? But by the same effect, you actually have sterics here, right? Because the methoxy, so this one's a little bit open. So you're going to get some mixture. It's going to be somewhere in between. It's not necessarily going to be specifically one or the other, but certainly we could, in more complex settings, perhaps get more sort of selectivity, right? If you can imagine several different groups throughout the ring, and maybe if we have time later on, we'll show some examples. You might actually be able to get a little bit more of a predictive nature in terms of high yielding. Yes. So right. No, you can't get meta. Ortho, meta, para. So right. So you get here and here, but not here. Yeah. Yeah, I was going to get to that, but yeah, your instincts are good. So just sort of thinking through the mechanism in general, we can also think about the attack in the mechanism as sort of, you can either think about it this way, or you can just sort of show a mechanism which might help explain it as well, right? And so if, say, for example, you were carrying out a reaction on toluene and you want to take this molecule and treat it with this acid chloride and aluminum trichloride, right? Based upon what you know over here, you get a mixture of compounds. But we can effectively do this through a mechanism as well, right? We can think about the fact that the sort of oxonium that we're going to generate, right, is going to react with this group. And again, it can react with this double bond as well. But if we just sort of focus on this one alkene here, and we start to think about the possible intermediates, right, we can sort of explain the chemistry through the intermediates as well. Right, because we have two possible outcomes during that first step. There's either this regiochemistry, or we have the other regioisomer. And so at least in terms of this one, it becomes pretty apparent, right? We're not going to be able to re-aromatize this compound. But as we start to look at the other positions on it as well, like the green, right? So this we're not going to form because it's not going to be able to re-aromatize. But some of these others, at least, we can begin to look at as well. Right, we can put the positive charge there, right? Wait, something wrong. Yeah. No, we're good. That's like. Right? And so here's a couple of the other possible compounds that we can get, right? So this would be the first attack, right? And as we look at these different molecules, right, again, here we have a carbocation on the sort of tertiary carbocation, right? What we'll see is that, for example, this compound, we can push those electrons over, right? This would put a carbocation at this position, right? So that's good, back to that tertiary one. But in this case, as we begin to push this around, and thinking about the sort of relative stabilization, right, we're going to be next to it. We're never going to be able to generate that, right, and then it's just going to go to the other one. We're never going to be able to generate that same tertiary carbocation. So, again, either of these ways, sort of, they both are just different ways to look at the same idea. Right, in the same way as we sort of showed before. If you sort of think about the intermediates that are forming, this isn't going to form again from that initial attack because, well, it can't re-aromatize, it's not really an option. this case, you're not going to have near the stability, right? But in both of these other cases, you're going to have that stabilization. So the product that you would get would effectively come from, again, the re-aromatization of those two compounds. But again, the selectivity being sort of ortho and para. So perhaps you want to just memorize this, but again, hopefully it's clear that you don't need to. And if you try to memorize ortho-para directing for a donating group, it's just going to be another one of many things to memorize. If you just think about the mechanism, it should make sense in terms of a donating group. Now, it was brought up previously. Yes, Margo? So we'll talk about that. We'll talk about that in a moment. Right now, what we're going to go to, well, halogens. Right. So we'll get to that in a second. So, because that's the sort of an interesting sort of twist to the rule. Okay. Okay. So it was just brought up electron withdrawing groups. Okay. And again, as sort of Margo just perhaps brought up as well, as we'll sort of follow up on this, there's a couple different electron withdrawing groups that we can have. And one of them, and they're both going to sort of deactivate and slow down the reaction a bit. But what's sort of difference between the two is that in some cases, electron withdrawing groups can actually be ortho-para directing, and in other cases, it can actually be meta-directing. And again, it's going to be a mechanism that's going to really help sort of explain this process. And so, whether you have, say, for example, an acyl group there, these are both electron, or say, for example, a chloride, okay? These are both groups that are both electron withdrawing in nature. So they're both going to be, both are going to be slower. Okay? But what's interesting about them is that in one case, you're going to get, in the top case, you're actually going to get meta-directing. So if you say, for example, treated this, we'll just stick with the sort of standard one there. In this case, what you're going to get to, and we'll go through the mechanism in a minute, so you're going to get meta. But in the case of halogens, what you're actually going to get to is ortho-para. Okay, so and again, there's some complexity within there based upon which halogens you sort of use, because certain halogens will actually donate in because the orbital overlap is a little bit better than the others. But I think the important point is to sort of not confuse things. Let's just sort of, we can at least cluster them all together, just because it doesn't really help things to sort of try to make disparity between the two. But in general, halogens will be sort of ortho-para directing as well. The reason in this case is, in the same way that when we had a methoxy there, we had those lone pairs that could stabilize, right? The chloride also has those lone pairs, okay? And so what you'll see is, if you could imagine drawing resonance forms, this chloride will put delta negative charge here, right? And a delta negative charge here, and a delta negative charge here. Again, through the resonance, because of the lone pairs on the halogen. But in cases where you have an electron withdrawing group, it's actually quite the opposite. And again, I want to get into nucleophilic aromatic substitution, so we'll just discuss. So this is just analogous. I'm not going to go through a full mechanism with the halogens. But this should be just analogous to what we've seen before. But it's just important to recognize that even though halogens might slow down the reaction because they are inherently electron withdrawing, they have a directing group effect in terms of the substitution. But I think it's worth it to just take a look again, just to sort of reiterate this sort of idea of delta minus and delta positive in the case of electron withdrawing groups where you have resonance. Right? So in cases where you have, say, a cyano group, or right? If you start to think about the sort of electron withdrawing group and where those relative dipoles are in charges, right? In the case of the green, we have a positive charge here and a negative charge here, right? And in the case of the sort of blue arrow, right, we're going to get the negative charge on the other carbon, okay? And so in this case, again, you can sort of notice the same thing that we saw with the acrylate earlier, right? On the left-hand side, we have a couple features about it, right? Again, you can sort of resonance stabilize that negative charge up on to that carbonyl, right? So that's going to make this a much more likely resonance form. Again, as would be the para position, right? If we push electrons down there, we would be able to see that as well. Here, we push forward here. Again, because we're not going to attack at this position, right? We're never going to attack necessarily at that position because then we can't re-aromatize. So really the ones that matter, where actually chemistry can happen, right, is this sort of form here, right, where we have that negative charge at the meta position. Again, here we have this issue that the carbonyl has a delta positive, delta minus, right? So this is in fact destabilizing carbonyls, even though it's more substituted. You have that electron withdrawing group where you're destabilizing that carbocation. And so again, you should be able to draw that parallel between electron withdrawing groups where you have that resonance destabilization and sort of aromatic chemistry. So in general, in a case like this, right, you're going to have the delta minus is going to be here and here, right? And so any chemistry that you get, like these are the meta-directed groups, right? That is going to be where you get the sort of chemistry. So, okay, does this make sense? So, again, slow down, take a look at the resonance forms, get comfortable drawing the resonance forms, look at which one's more stable than the other, and you should effectively be able to sort of show where that negative charge is. And again, you could also do it the way that I showed in terms of show the intermediates of the first electrophilic attack. And it's effectively going to be the exact same idea, exact same concept, but just looking at it a little bit differently. Okay? All right, so for the remainder of the class, we're going to talk about a slightly different type of, so we focus primarily on electrophilic aromatic substitution chemistry. So all these cases of meta-ortho-directing have to do with the fact that we're taking these molecules and these aryl groups and we're treating them with electrophiles. And so the aromatic groups are effectively serving as a nucleophile. Okay, so again, it's electrophilic aromatic substitution. But as we've seen, right, alkenes, we started, alkenes are one of the early nucleophiles that we saw. Right, so again, alkenes were one of the early molecules that we saw in terms of them behaving as nucleophiles. Right? But in the same way, we've also seen chemistry recently this semester where we've seen alkenes serve as an electrophile. Right? And what were these cases where we saw alkenes behaving as electrophiles? When have we seen nucleophiles attacking an alkene? Right, Michael chemistry, Michael additions, right? So if you think back to earlier on in this chapter, or the semester, right, we saw instances where enolates would add into a conjugated diene, right? And this effectively represents an instance where we've seen an alkene, right? Alkenes as an electrophile. Okay. You guys remember this. And so it turns out that the chemistry that we see in aromatic systems also has this sort of complementary value, or complementary usage, I should say. And oftentimes when it works, it's for this sort of same idea. What we're going to see is in nucleophilic aromatic substitution, we're going to see what effectively amounts to masked, I like to call it masked Michael additions. So a Michael addition masked, or a sort of a 1,4 addition masked within a benzene group, right? And so this is one case that we'll see a lot, right? And so if you have a molecule that has the ability to sort of stabilize a negative charge through resonance, right? If you sort of have a masked sort of a masked enone, for example, or if you have all this well, right? We have this sort of parallel here where we have a nitro group, right? These are instances where we've seen in the past 1,4 addition can take place, and again, it has to do with the ability to have a nucleophile add in this sort of fashion and kick up into those sort of into the pi bond here. So again, here in the case of say for example a ketone, or here in the case of a nitro group. And so as it turns out, if we have molecules that are like this, one of the things that we can do is we can begin to perform substitution chemistry. Now here's the issue, right? It's a little bit different mechanistically, and there's a factor on this that makes it perhaps a little bit different. I'll try to explain this in a moment. To do electrophilic or nucleophilic aromatic substitution, in general, what you need, this will help direct groups a bit, but you need some type of a leaving group, okay? So for example, a leaving group at that position. And the reason is, if you add a nucleophile into this system, previously, what we were able to do is the sort of conjugate base would in fact come off and pluck off the group. But in this case, if we have a negative charge there, right, it's got to kick back out, right? And if the nucleophile is able to add in and there's not something better that could leave, what will happen is you'll just go in the reverse direction, right? So if there's not a leaving group there, once the nucleophile adds in, right, the lone pairs will just kick it back out. And so nucleophilic aromatic substitution generally needs to be a type of exchange. You have some leaving group on there, right? So it's analogous to Michael to an extent, but in a Michael reaction, right, you don't regenerate the alkene, right? In a Michael reaction, you don't regenerate the alkene. And so in this case, the molecule is going to want to regenerate that aromaticity, right? So you can't just add 1,4 into an aromatic group necessarily, because you want to then be able to regenerate these sort of the aromaticity. So the leaving group will effectively serve as the way to get exchange. And one of the benefits to this is that you have a certain ability to, well, I mean, there's the downside compared to electrophilic aromatic substitution is that you need to sort of install that group there in some way, right? That's the sort of downside to it. But on the plus side, what you have is a little bit more of a directional element to it, right? If, say for example, in this case, let's say for example, in this case, if instead of adding sort of 1,4, if we added, for example, 1,6, right? It's going to become very difficult, right? If you add 1,6, what you're not going to be able to do is add back in, kick out this leaving group, right? You can't. There's no way you can now push these electrons and go and kick out the group, right? So what's going to happen is this will simply be reversible, and eventually it'll funnel through the pathway that'll lead to the appropriate product. So in nucleophilic aromatic substitution, in general, what you end up having is some type of a leaving group. And so, again, what this leaving group is, I think the book will discuss halogens often because that's the one that we'll use, but you could imagine, for example, a tosylate. In terms of the chemistry happening, we've seen it in our lab with things like a methoxide. Like we made this discovery recently where we were doing electrophilic aromatic substitution and methoxide was leaving. So, as long as something can leave, you can start getting into nucleophilic aromatic substitution. So this type of chemistry that we're showing here, again, the book will discuss with things like amines. You can imagine it with alcohols. You can imagine it with sulfur-containing molecules. So really anything with lone pairs and acetoxy groups. So your sort of standard players of nucleophiles could, in principle, do this chemistry. And so if you have a system, the important thing to recognize is if you have a system like this with an electrophile or chloride in place, you can swap out that chloride with perhaps the group that you would want in a synthesis problem. So you could use an amine, you could use alcohols, you could use iols, and so on and so forth. And so if you simply go through the mechanism, and it has lone pairs, and you can sort of eventually fulfill, so it's probably have a proton on it, so you can deprotonate it, it should be okay. The one other type of nucleophilic substitution, which is actually kind of neat, so this is just sort of analogous to Michael, so this is the one that I wanted to show first. One last thing to bring up here. With this type of chemistry, with nucleophilic aromatic substitution chemistry, we talked about the sort of relative selectivity. But one of the things that you should sort of notice is that what's not going to work that well is if, say, for example, you have a chloride at that position, or you have a leaving group at that position, right? And let's say you took this molecule and you tried to treat it with, let's say you were trying to take that chloride and you were trying to switch it out with ethanol, right? The problem here, again, comes back to thinking about where the electrophilic sites of this molecule are. You can add 1,4 here, right? And you can add 1,4 here, right? And so these are effectively delta positive sites. But at this position and this position, what it is a delta minus. Okay, so these are not, again, if you try to push the electrons through that system, what you'll see is you'll never be able to delocalize those electrons up into that pi system, right? If we take that nucleophile, right? It'll jump between a couple of these positions, but where it will never go up into the carbonyl. So this attack will actually this attack will actually never happen. So you'll never actually, so in electrophilic aromatics, nucleophilic aromatic substitution, you need to really think about that mechanism of a 1,4 addition. You have to think about the fact that you need a way to add in that sort of leverages this sort of ability to sort of stabilize the impending negative charge from that sort of conjugate addition. Okay, so in this case, you can do ortho, you can do para, but meta is not going to work well in this case. Again, you sort of look through the mechanism, you should be able to see that that at the meta position, you just don't have that same type of 1,4, 1,6 addition. Okay, so hopefully this makes sense. Yeah. Oh, meta to the. So if you have a chloride and an acetoxy that are meta, you won't be able to do it. The chloro has to be ortho or para to exchange it out. So what I mean is, so if this is electron withdrawing group and this is leaving group, yes, that will work. You can do electrophilic or nucleophilic aromatic substitution. Leaving group, no. Yes, right? So if you have the leaving group ortho to the electron withdrawing group, and when I'm saying electron withdrawing group, I specifically mean electron in terms of like resonance stabilizing. So a ketone or a nitro, an ester, sulfonic or sulfonic acid even, something that can resonance stabilize. If it's ortho, you can switch out that leaving group with something else. If it's para, you can switch it out with something else. But if it's meta, you're not going to be able to, or it's going to be much more difficult to. Okay? And that's through a mechanism that involves this type of nucleophilic aromatic substitution that's analogous to Michael chemistry. All right, so
When you say it'll make you go slow, does that mean that you even smaller nucleophile?
well, that means that I never say something will never happen. Yeah, that's the sort of scientist in me. Yeah, no, you would never want to plan that around synthesis, but chemistry always fools us. So, okay, so the one other type of nucleophilic substitution that's actually really cool, and I'll tell a fun story when I'm done with this, involves sort of benzene. Okay, so let's see what the book uses. So it turns out it was sort of discovered back in, I think, like the early 1900s, that if you take like sodium and ammonia, so this sort of sodium amide, and you which is a really strong base, and you treat it with some type of an aryl chloride or an aryl bromide or something like this. What was discovered, in fact, is that you can actually the book shows sodium hydroxide, but in this case, it was sort of discovered that what happens in this reaction is that you can start to get substitution of this molecule. So you can begin to get these. You can actually, in a way, exchange out the chloride with the amine. Okay. Now, as we sort of just mentioned, right, an amine is not just going to add into a general chloride, right? It doesn't have that electron withdrawing group that would be able to stabilize it. But when you have a really strong base, at least in principle, and there's other ways, and I'll tell you guys about these in a moment, what can actually happen, and you guys are all going to be prepared to have your minds blown. you can generate a molecule known as benzene, okay? Right? So this is a molecule known as benzene, okay? So you guys should all be looking at this molecule and saying, no, you didn't draw that. Because you can't generate cyclohexane count, you can't generate an alkyne, right, in a 6-membered ring, right? What would happen if you tried to generate this molecule? What are the reasons why we wouldn't want to generate that molecule? Well, yeah, it's unstable, but that's a sort of cyclical argument. Yeah, the ring strain, right? If you have a standard alkyne, right, it wants to be 180 degrees, right? And what you've done here is you've effectively torqued it to the point where it's super strained. You've taken a bond that wants to be 180, and you've effectively put it in this position where you have, whatever it is, 120 degrees. So you brought it way out of the bond angle that it would normally want. So it turns out that even in like cyclohexane, there are ways to sort of make it, but it's not going to be stable. Like it's sort of made and used. The largest sort of stable cyclohexane, the sort of the largest cyclical alkyne you can actually generate is the 8-membered ring, cyclooctane. But even in the case of cyclooctane, so 8-membered, cyclooctane is like it's also very reactive. It just happens that you can actually isolate it. And so again, this is highly unstable. And one way that you can sort of think about it yeah, exactly. So you don't isolate benzene. What you do is you make it what we say in situ. But the chemistry will effectively react in more of this sort of polarized form. Like which of these two it actually exists in is perhaps debatable, right? Does it exist as the alkyne? Does it exist in this sort of zwitterion form? Well, it's probably something in between. It's not really one or the other. But we can begin to explain some of the chemistry that happens from this intermediate that we've shown here, okay? And so perhaps what I should sort of say is this. And again, we'll work it up and generate the amine, but perhaps in terms of a mechanism, it's better if we draw the product like this. And so what will happen is, again, it's nucleophilic aromatic substitution. What effectively will happen here now is that we have a sort of a cation species, which is a highly electrophilic center here. Okay, that's going to attack. Right, and you have that negative charge over there, and that's going to go into protonate. And again, it could be intermolecular, it could be intramolecular, but the point is that the sort of net process is that you're effectively adding the sort of nitrogen amine bond across that triple bond. Okay, and then again, you work that up. This is going to react upon workup. So like aqueous workup, aqueous quench, and so forth, you'll end up getting the amine. And it turns out that similar type of chemistry can take place under really high pressure, really high heat with some other bases as well. For example, sodium hydroxide isn't just going to react with chlorobenzene. This is not chemistry that you would necessarily just set up in a hood and get it to go. You would need probably super pressurized system, probably very high heat, because again, this is going to be a very, very high uphill process. Yes. So right, so if instead of sodium amide you added sodium hydroxide, you could also switch that out as well. But you need really, and with this you would as well. You need sort of really high heat, you need really high probably pressure as well to get some of this chemistry to take place. So this isn't really the most practical sort of chemistry in the world. What's that? Oh yeah. Just say high pressure and heat. So anyway, it's a sort of interesting just sort of follow-up to benzene. In general, because this is such an uphill process, we have other ways, and this is early in your book, but we have other ways that are a little bit more mild to generate benzene and benzene precursors. And some of the molecules that you can make that are not necessarily isolatable but you have molecules such as this one here. I'm trying to think. Actually, it's not this that you start with. I think it's the acid. And then there's a counterion to this, so I think it's like X minus or something like that. So you'll start with molecules like this, right? And what you'll do is you'll take a molecule like this and you'll treat it to base. And what'll happen is you'll generate the right, you'll generate that carboxylate, okay? And now what you see is you have, you can generate CO2 to generate a negative charge, right? You can do that sort of decarboxylation, right? And then right next door, you have a fantastic leaving group, right? That's that nitrogen, right? That's also a gas. Right? And that can actually lead to your benzene. It turns out that this is sort of a much more common way to get to intermediates like benzene. But again, it requires being able to make compounds like this that's sort of rather difficult. The reason I wanted to sort of tell you guys about this entry is that I've done this chemistry once in my life. And, well, a couple times, but all within probably a 1 or 2 week period. And it was back when I was a postdoc, and it was my first year, and we were considering trying to get benzene intermediates to react with things. And as you look at this, do you guys know like when a molecule is like explosive? Do you guys know why molecules are explosive? What's that? Who's what? Well, stability is one thing, but yeah. So there's an energy release that's certainly associated with a lot of them, but there's something else. Yeah. So that would be reactive. That would be along the lines of reactive. But what's happening in an explosion? What's really happening? You're generating a lot of gas. You're going from a very small volume to a very large volume very quickly, right? And so if you have something that's a solid, and a reaction takes place, and it generates gas rapidly, right? And say, for example, you have that in a container, right? Suddenly you are rapidly expanding the pressure in there, and it's just going to blow up, right? And so a lot of like compounds that we think of as like TNT, for example, which is tetranitrotoluene, which now you can all probably draw it. Because you know what toluene is, and you just put 3 nitros in there, and you can guess, right? Take toluene, treat it with nitric acid and sulfuric acid, and it's going to be directed orthopara, right? So now you all know how to make TNT. Great. All right. But the process of that breaking down is such in a way that you're generating things like I think it's the nitrous oxide gas. And then because of the temperature, you also have benzene, which at the higher temperature is generated by the energy, is also a gas. So you have all these things that immediately go from a crystalline solid to a gas very quickly. And when you look at this compound, right, it has that first artifact of that doesn't look too stable, right? And it has this factor of one gas being formed, and you have this other factor of another gas being formed. And what it leads to is a situation where you have like 2 blast shields set up in front of you because you're nervous it's going to blow up, and you're trying to reach around with gloves working with this because you don't want to lose your hands. And And so I actually made this stuff and was working with it, and it was terrifying. But what was neat was at the very end, I cleaned up everything. I didn't kill myself, which is why I'm here. The reaction never ended up working, so it didn't really matter, but I guess it was worth a shot. But what I did was, I didn't realize, but I had a little bit of the compound, just a tiny, tiny bit, probably like a milligram or so. It was on the tip of a spatula. And these molecules are shock sensitive, right? And so all it takes is a little bit of friction, right? And so I had it on the bench and didn't realize it. And I was going through and I started cleaning stuff. And I forget what happened, but I saw like some of it like got on the table, and I saw, and I just didn't think that it was this compound, and I just scratched it a little bit with my spatula, and it scared the hell out of me. It was this tiny little mountain, but pop, like you know the little poppers that you throw. It wasn't like an explosion or everything, but it was this really fine and kind of very scary, just pop, which was this exploding very quickly. And again, and I stopped working on that chemistry because I didn't trust myself. But anyway, so this is just another way that you can get into benzene, and certainly benzene is highly strained. You do Diels-Alder chemistry with it, and so forth. So again, we've learned a couple different types of nucleophilic aromatic substitutions. One is through a benzene intermediate, and maybe this story will help you remember benzene. And the other one is analogous to myclone. So today's class, again, just to sort of summarize, electrophilic aromatic substitution is regioselective, and pay attention to the resonance form. So I expect you guys to all be able to sort of understand the regiochemistry of electrophilic aromatic substitution. And then in terms of nucleophilic aromatic substitution, we learned a couple different ways. One last comment. So I brought this up. I'm going to start posting some signs probably today after office hours. But again, I think it's a really nice opportunity on Friday. Stuart Legreese, who's an NIH investigator, also a collaborator of mine, one of the world's experts on HIV, resistance pathways and drug development stuff. He's going to be giving a talk at 2:30 to 3:30, and before that at 2 o'clock in the same lecture hall, we're going to sort of open up some time for him to talk to undergrads, and so you can show up. We'll have a sort of a round table if you guys want to ask him questions about his career and so forth. Just get a chance to meet him. I think it's a nice opportunity because it's so related to sort of drug development. I know a lot of you guys have interests in biomedical fields. It's a good opportunity. He's kind of a big deal. So, all right. Anyway.